Welcome back to the Deep Dive. Today we're zeroing in on something really critical if you're looking to really master welding inspection. It's our CSWIP 3.1 exam prep series. And look, this isn't just about memorizing answers, right? It's about truly getting the mechanics behind a good weld and, equipping you with that critical thinking you absolutely need for the certification.
Exactly. It's about understanding the why, not just the what.
Precisely. So our mission today is pretty straightforward. We're going to tackle 5 crucial multiple-choice questions, the kind you might actually see pop up in the CSWIP 3.1 exam. But like we said, the goal isn't just spitting out the right answer. We want to dive deep into why it's the right answer. Look at the nuances, the common traps, and what it all means out there in the real world.
So you're not just informed, you're actually insightful. That's the key difference.
Totally. Think of this as maybe a shortcut to getting your head around those tricky welding fundamentals. We've got questions touching on everything from, say, the root bead intricacies to the practical side of measuring fillet welds.
Yeah, these are the foundational bits that really separate, a decent inspector from a truly great one.
Okay, let's get right into it then. Our first question. For full penetration, single-sided butt joints, root bead penetration and profile are mainly influenced by, and the options are A, root face, B, bevel angle, C, root gap, D, included angle.
Okay.
So when you think about nailing that perfect root bead, getting that consistent penetration, that shape, what factor really jumps out as the main driver?
Well, it's interesting because they all play a part in the overall joint design, but for that specific outcome, the root penetration and profile, the correct answer definitely is C, root gap.
The root gap.
Yeah, the root gap is absolutely paramount. It's crucial for both getting the penetration you need and forming the right profile on those single-sided joints.
Why is it so critical compared to the others?
Think of it like this. You're setting up a channel, almost like a funnel, for your arc and your filler metal. An optimal root gap gives you the right access. It lets the arc melt fully through the joint thickness, giving you that complete root fusion. And, just as importantly, it provides just enough space for the molten metal to form a nice, consistent bead shape underneath the root profile.
So it's like a Goldilocks situation. Not too big, not too small.
Exactly that. If the gap's too small, you risk bridging. The metal struggles to get through. You might get insufficient penetration, maybe even lack of fusion.
Okay.
But if it's too large, well, then you've got the opposite problem. The molten pool doesn't have enough support and can just fall right through. That's burn through.
Ah, okay. We'll probably come back to that one.
Yeah. So for an inspector, that root gap is often the single most critical thing a welder controls before striking the arc. It really should be your first check on a prepared joint.
That makes a lot of sense. That idea of it being the access channel really clarifies it. But I'm wondering, what about the other factors then, like bevel angle or included angle? They're not totally irrelevant, are they?
Oh, absolutely not irrelevant. They're all interconnected, definitely.
Right. Don't they sort of indirectly affect how easy it is to get that root gap right, or maybe how the heat focuses?
They do influence it, yes. The bevel angle and included angle, they define the overall joint geometry, how much weld metal you need. And yes, they definitely impact arc accessibility and how the heat distributes, which, in turn, can make it easier or harder for the welder to maintain the gap and get the penetration.
Okay.
Like a really narrow included angle might make it tough to get the electrode in there properly, maybe leading to the lack of sidewall fusion higher up.
Yeah.
But when we're talking about the primary control over the depth of penetration and the bead shape right at the root, the gap is king.
Got it. So the inspector checks the angles during prep, but keeps an eagle eye on that gap right before welding starts.
Precisely. That gap is the final decider for that crucial root pass.
Okay. So we established the root gap is key for getting the weld through, but sometimes even if it gets through, it doesn't quite fuse properly. Is that right?
That's another common issue, yes.
Yeah.
Incomplete root fusion.
Which brings us neatly to our second question. Let's see. Incomplete root fusion in a single V-butt weld may be caused by. Options are A, linear misalignment, B, root gap being too large, C, root faces being too small, D, welding current too high.
Right. So now we're talking fusion, not just getting through.
Exactly. What's the most direct cause here for that lack of proper merging at the root?
This really highlights the need to differentiate these defects. They sound similar, but the causes can be quite different. For incomplete root fusion, the most direct cause listed here is a linear misalignment.
Linear misalignment. Okay, explain that. How does that stop fusion?
So linear misalignment, sometimes called high-low, is basically an offset. One plate edge is higher or lower than the other along the joint.
Ah, okay, like a step.
Exactly. It might look small, but it's really detrimental to the root. Think about trying to glue two bits of wood edge to edge, but one's slightly proud.
Right, the surfaces don't meet properly.
Precisely. In welding, even with perfect heat and filler, that physical offset means the molten metal from one side literally can't properly merge or fuse with the molten metal from the other side right at the root.
So the base metals just don't get a chance to mix completely down there.
Correct.
Yeah.
The other options tend to cause different problems. A large root gap, as we said, leans towards burn-through.
Yeah.
Small root faces might cause excessive penetration. High current could cause burn-through or undercut. But that specific issue of fusion failing at the root points most directly to that physical misalignment.
So it's not just about heat and filler, it's the actual physical setup of the joint before you even start. This really underscores the inspector's role in checking the prep work, doesn't it?
Absolutely critical.
What's the first thing an inspector does to check for that, just visually?
Primarily, yes. That initial visual check of the fit-up is paramount. Before any welding, you'd use, say, a straight edge or a dedicated misalignment gauge across the joint. Even a small step is a potential red flag. It needs correcting before welding. Because trying to fix incomplete root fusion caused by misalignment after the fact, that's often difficult, costly, involves back gouging. It's a classic case of prevention being way better than cure.
Definitely sounds like it. Okay, on to question 3. And this one, again, has that subtle but really important difference. We're talking penetration now, not fusion. Incomplete root penetration in a single V-butt joint may be caused by options. A, excessive root face. B, excessive root gap. C, the current settings being too low. D, both A and C.
Right, so now we're focused purely on whether the weld metal actually made it all the way through the joint thickness.
Exactly. What's stopping it from getting through?
This is a great question for cementing that difference. Incomplete fusion is about joining. Incomplete penetration is about depth. And here, the correct answer is D.
Both A and C.
Both A and C, so excessive root face and low current.
Yes. Let's break that down. First, an excessive root face. That's the flat land at the bottom of the V-groove, right?
Yeah. If that land is too thick, it creates a physical barrier. It's just too much material for the arc energy to melt through completely.
Okay, like a roadblock.
Pretty much. You might get fusion on the sides, but the weld just won't go all the way through the full thickness. It's physically blocked. Then you have low current settings. That's straightforward, not enough power.
Right. Insufficient heat.
Exactly. If your current is too low, the arc simply doesn't generate enough heat to melt the base metal fully through the root, regardless of the root face size.
So one's a physical block, the other is a lack of energy.
Precisely. Both work together or independently to prevent the weld metal from fully extending through the joint thickness. And notice option B, excessive root gap. As we discussed, that typically leads the other way towards burn-through, not incomplete penetration.
Right, it goes too far, drops out.
Yeah.
This raises a really practical question, though. Given how similar incomplete fusion and incomplete penetration sound, how do inspectors quickly tell them apart in the field? Especially if you can't do destructive testing right away. What are the visual clues?
That's a really good question because visually it can be tricky, and sometimes they do occur together. But there are telltale signs. For incomplete root penetration, the most obvious sign, especially on a single-sided weld, might be the complete absence of a root bead on the backside.
Okay, nothing came through.
Or maybe a very narrow, inconsistent, sucky-looking bead. It's fundamentally about the lack of material making it through. Sometimes you might see concavity at the root from the front.
And for incomplete fusion.
Well, with incomplete root fusion, you might actually see a root bead on the back. It might look like it penetrated. But a trained eye might spot subtle things like sharp notches where the weld meets the base metal or a lack of smooth blending. It might look cold.
Like it didn't quite wet properly onto the base metal.
Exactly, a cold lap. Where the molten metal flowed against the base metal but didn't truly merge with it. Often, though, definitive proof of incomplete fusion, especially if it's internal, requires NDT like RT or UT. But checking for misalignment beforehand helps prevent it. And for penetration, that visible lack of a root bead is a strong clue.
Got it. Okay, we spent a lot of time on butt joints and root issues. Super important. But obviously, a huge amount of inspection work involves fillet welds. They have their own rules, right?
Absolutely. Different geometry, different measurements.
So switching gears a bit. Question 4. For fillet welds, it is normal practice in the UK and USA to measure options A, throat thickness, B, leg lengths, C, penetration depths, D, both A and C.
Okay, a practical question about standard practice.
Yeah, what's the standard everyday measurement for fillets in these regions?
This one's fairly straightforward based on industry norms. The standard practice is to measure B, leg length.
Leg lengths. Why leg length when things like throat thickness sound more structurally important?
Well, you've hit on a key point there. Throat thickness, that shortest distance from the root to the face, is theoretically the most critical dimension for strength. That's what bears the load. But measuring it directly and accurately on a finished weld, that's actually quite difficult without cutting the weld open or using specialized gauges very carefully. It's an internal dimension, often obscured by the weld profile.
Okay, practicality wins out.
Largely, yes. Leg lengths, on the other hand, are the distances from the root out to the toes of the weld on each plate. They form the sides of that right-angle triangle.
Easy to get a gauge on those.
Much easier. Standard fillet weld gauges are designed specifically for measuring leg length quickly and reliably. It makes routine visual inspection, QC checks, much more practical.
And specs usually call for leg length.
Exactly. Welding procedure specifications, WPS, and engineering drawings typically specify the required leg lengths. The inspector then verifies these using a gauge. Penetration depth, like throat thickness, is also internal and generally requires destructive testing to measure accurately.
So it seems like practical simplicity is the driver here.
It is. While the engineer calculates strength based on the throat, the inspector verifies compliance by measuring the legs.
That does raise another point, though. If the throat is what really matters for strength, but we mainly measure the legs, isn't there a bit of a compromise there? How do we know the throat is actually sufficient?
That's a very astute observation. It's a fundamental aspect of how welding design and inspection work together. Engineers absolutely design based on the required effective throat thickness. That's non-negotiable for load capacity.
Okay.
However, they build the practicality of measurement into the system. Design codes and standards provide relationships, formulas, or tables that link a minimum required leg length to achieve a certain effective throat thickness.
Ah, so there's a known correlation.
Precisely. These relationships usually assume a certain minimum root penetration and a flat or slightly convex weld face profile. So, when an inspector measures the leg length and confirms it meets the specified minimum, they are indirectly confirming that the required effective throat thickness has, by design correlation, also been achieved or exceeded.
So it's an engineered workaround, essentially. Specify something easy to measure that guarantees the harder to measure critical dimension.
You've got it. It's a well-established engineering practice. The inspector's job is to ensure those specified leg lengths are met, knowing that this underpins the design's integrity via that established relationship.
Makes perfect sense. All right, we're on to our final question now. This takes us back to a defect we mentioned earlier, often linked to that root gap issue. A burn-through may occur if the absence A, current is too low, B, root face is too large, C, root gap is too large, D, arc voltage is too high.
Burn through. Yes, the welder's nemesis sometime.
Definitely sounds frustrating. So think about what causes that excessive heat, or maybe more importantly, that lack of material support underneath. What makes the molten pool just drop?
Yeah, it's incredibly common, especially on root passes or thinner materials. And you're right, it's often about that lack of support. I remember one job, tight deadline, naturally, and a batch of prepared plates came through where the root gaps were consistently just a fraction too wide.
Oh dear.
Yeah, the welders were fighting burn through constantly. Molten metal literally dripping through caused huge delays, porosity issues, the lot. The culprit, time and again, was that oversized gap. So the most direct cause here is undoubtedly C. Root gap is too large.
Okay. Explain the mechanism again. Why does that gap cause it?
So imagine the arc melting the metal. You need enough solid base material underneath that molten pool to hold it up, right? Against gravity and arc force.
Makes sense.
When the root gap is excessively wide, there simply isn't enough underlying material there to support the puddle. It's like trying to bridge too wide a chasm with something liquid.
It just falls through the middle.
Exactly.
Yeah.
The heat from the arc melts the edges, but there's nothing substantial underneath, so the molten weld pool literally falls or bends through the joint, creates that hole. Now look at the other options. Low current, that causes lack of penetration.
Right.
Large root face, B, again, lack of penetration usually. The arc can't get through the thickness. High arc voltage, well, voltage affects arc length and width. Very high voltage can increase heat input overall, potentially leading to excessive penetration or undercut. But it's not the primary direct cause of the pool physically falling through due to lack of support. That's the gap.
So fundamentally, it's about that balance, having enough material there to contain the heat you're applying. Too much gap, and you're essentially welding on thin air, and gravity wins.
That's a good way to put it. Finding that sweet spot between the gap, the root face, and the welding parameters is key to avoiding it.
Wow, okay. We have covered some really, really critical ground there for anyone prepping for the CSWIP 3.1 exam. From those, subtle but vital differences between fusion and penetration issues, right through to the practical side of why we measure fillet legs, these questions really show the depth you need.
Absolutely. And if you connect this to the bigger picture, these aren't just abstract exam points, are they? They are the absolute bedrock of ensuring structural integrity, ensuring safety, making sure welded components perform as designed. Every single one of these parameters matter.
Yeah.
Understanding the why behind defects like burn-through or incomplete fusion, or knowing why leg length is measured. That critical thinking is what transforms someone from just looking at welds to truly inspecting them effectively.
Couldn't agree more. It's about anticipating issues, diagnosing them correctly, ensuring quality right from the start. So as you listening continue on your journey towards becoming a certified welding inspector, maybe leave you with this thought. How will understanding these specific causes, these effects, these practicalities we've discussed, how will that change how you approach your next inspection task? It's not just about passing the test right. What will you look for differently now?
That's the real takeaway, applying this knowledge.
Definitely something to think about. We'll leave it there for this deep dive. Thanks for tuning in.